I'm working on the railroad all the livelong day. Hey guys, Coach Carroll back here. I should have been a professional singer. People tell me that all the time, but I didn't do it. Okay, here we have a problem involving a vector in 3D. Okay, so in case you ever find yourself working for a railroad company or you're just needing to pass my class, this might be helpful for you. Okay, so the problem says that an overhead crane is used to reposition the boxcar. There's the boxcar within a railroad car repair shop. Okay, if the boxcar begins to move along the rails when the X component of the cable tension reaches 600 pounds, calculate the necessary tension T in the cable. Okay, so we don't know the magnitude of the tension that the crane is actually pulling on this cable with. Okay, so that's actually what we're looking for there. But we do know that this cable car actually begins to move when the X component of the tension vector is 600 pounds. And so we want to know, okay, what magnitude do I have to pull in this direction to actually give me an X component of 600 pounds, because that's when the railroad car will actually begin to move along the track this way in the X direction. Okay, so we know this. We know the X component of the tension vector. So if we can find the direction from these ratios that we're given here, then we've pretty much got the problem. Now, this problem, the 3D component, sometimes confuses students a little bit. So let's simplify the problem. This is a good problem-solving strategy. If you don't know what to do, try to simplify the problem and start out with something that you do know, and then add a little bit of complexity. Okay, let's say the problem looked like this. So I'm just going to make this problem a 2D problem. Okay, so basically I'm going to take this problem and project it onto this XY plane over here. So I'm going to say that the tension vector is not actually pulling any in the Z direction. So I'm going to get rid of that 1 there. So let's say this is 5 and 4. I'll draw a coordinate system here that I'm dealing with. There's X, and there's Y. Okay, so now here's a 2D version of this problem. It's not the same problem. Okay, what I'm doing is I'm just simplifying the problem so that hopefully you understand the 2D version, so the 3D version then is not very difficult for you. Okay, so in this problem, now in my simple 2D version of the problem, let's say they ask us, or they tell us the same thing. They tell us that when the X component, so when the X component of the tension vector reaches 600 pounds, then the car begins to move in the X direction. So what is this tension T to actually give us an X component of 600 pounds? Well, from this ratio, we've used these ratios before, I can find what's the X component. I can find what's the X component of the vector. So I could find the X component of the vector by taking the magnitude T times, now this leg 5 of the right triangle here is actually parallel to the x-axis. So if I'm taking 5 divided by the length of the hypotenuse here, and the hypotenuse has a length of 5 squared plus 4 squared. So this component here, all that is the X component of the tension vector. Okay, and so this would equal 600 pounds, and here's one equation, one unknown. I can solve for T here. Okay, now you say, well, what's the difference between this simple 2D problem and now our 3D problem here? Well, the only difference is that now this tension vector actually has a little bit of a z component to it in this direction. It's just over a unit of 1, okay? But we're going to apply the same principle to solve it. So we know the x component of the tension vector is 600 pounds, and I can find the x component of this tension vector by taking t times, what's the length here parallel to the x-axis? It's a length of 5 divided by then basically the hypotenuse here. It's a 3D hypotenuse, that's alright. 5 squared plus 4 squared plus 1 squared. Okay, so now here's one equation with one unknown there, t. I can solve that equation for t. And t comes out to be 778 pounds. Okay, so when you pull with a tension of 778 pounds directed up in this direction, defined by these coordinate directions, then the x component of the tension vector reaches 600 pounds and the car begins to move in the x direction. Okay, so let's look at the second part of the question now. The second part asks us to determine the angle theta xy between the cable and the vertical xy plane. Okay, well, you've seen problems similar to this. Okay, problems that we've solved similar to this ask us to find what's the angle between t and maybe the positive y-axis, theta y, and you've solved those problems by using the direction cosines. Alright, where if you're looking for an angle that a vector makes with, let's say, the positive y-axis, you can do that by taking the inverse cosine of the y component of the vector divided by the magnitude of the vector. And let's say if you want to find the angle tension makes with the positive x-axis, you can do a similar procedure. Okay, but this question is a little bit different because they don't ask for the angle that the tension vector makes with any positive axis. They actually ask the angle that the tension vector makes with a plane, with this xy plane back here. Okay, now I'm going to draw this problem in a little different orientation that may I think will help you see better what's really going on. Okay, I'm going to draw the xy plane down here. So the xy plane is kind of like the ground down here now. Okay, and let's say the z direction is coming up here then. Okay, now I'm going to sketch a tension vector. Okay, now let's say if I were to project this tension vector onto the xy plane, and this tension vector is actually out here. Extend that out. Okay, so if I project this tension vector onto the xy plane, this is the line that I get here. Okay, now notice this is not parallel to the x-axis, or it's not along the y-axis either. Okay, so the angle that they're actually asking us for in the problem is actually this angle here. That would be the angle theta xy that they're asking us for in the problem. Okay, now hopefully when I drew that, maybe you got an idea of actually how to solve the problem. If not, we'll try to lead you to the solution here. Okay, let's start out with something that we do know, something simple. What's the angle between the z-axis and the x-axis? Well, you say that's easy, that's 90 degrees. Okay, what's the angle between the z-axis and the y-axis? Well, that's easy, that's 90 degrees as well. What about the angle between the z-axis and any line in this xy plane, such as the projection of the tension vector onto the XY plane, well, that angle there, what's that? You know, that to also be 90 degrees. Okay? So hopefully you see it now that this angle between the z-axis and the projection of the tension vector onto the XY plane, that's a 90-degree angle. Okay? And can I find this angle? Let's say that's the angle theta z. That's the angle the tension vector makes with a positive z-axis. Yeah, we can do that. That's theta z we can find by using our direction cosine. So I can find the z component of the tension vector, divide it by the magnitude, take the inverse cosine of that ratio, and I'll find theta z. So then, easy enough to hopefully you see now that then theta xy can be found by just taking 90 minus theta z, and we've got our answer there. Okay? Very good. So now let's just do the boring algebra part. What is tz? Okay? tz. So we're solving for theta z here. Cosine inverse tz is whatever the magnitude of the tension vector is, times, now this 1 is in the z direction, this side of our ratio here, side of our coordinate direction, it's parallel to the z-axis, so 1 divided by 1 squared plus 5 squared plus 4 squared. That's the z component of the tension vector divided by the magnitude of the tension vector. And you see what happens. Tension vectors cancel. Now I have the cosine inverse of that ratio there, and I can get an answer for that. Theta z, theta z is not 8.8. Once I solve for theta z, plug that into this equation here, then theta xy comes out to be 8.88 degrees. There you have it. Okay, so hopefully you see in this problem that a good problem-solving method is to draw a picture. Okay, draw a picture so you can try to see what's going on, and even if you don't know exactly how to get the final solution right away, start trying to simplify the problem, such as I did in this first part here. I simplified the problem down to a 2D version of the problem. Solve that because we've seen how to work with ratios, with the right triangle ratio in 2D before, and then it wasn't that hard to make the connection just to add the z component here. Okay, so try to simplify the problem, draw lots of pictures. I think that will help you solve problems that you think you don't know, but when you try it, I think you'll find out that you actually do know it. All right, guys, have a good day.